And welcome back to the final podcasts for Chapter 14. So we're going to talk about things like reaction mechanisms and catalysis. That's a great word. But just kind of the how do reactions take place. So the idea of collisions and whatnot. So first of all, we're going to sort of start talking about reaction mechanisms. And the idea that reactions happen through a series of individual steps. Individual steps. So recall from our prom date extravaganza that for a reaction to take place at all, you have to have some collisions. And so just because you have one collision doesn't necessarily mean that you're going to have a reaction take place. There's lots of different variables that affect if a reaction will take place, and we'll get to that in a little bit. But in terms of the series of steps, I don't know if you've ever given much thought to all of this, but when these molecules collide, do they just sort of how do they break up and how do they rearrange and all that sort of stuff? And that's the idea behind a mechanism. So there's three different types of steps. A unimolecular mechanism just basically means that you've got one chemical that disintegrates. Disintegrates. So like a decomposition reaction, so whatever, chemical species A breaks up into B and C. So you just got one reactant there. Bimolecular, you're going to have two things colliding. So it could be like A plus B gives you C. Or it could be A plus A. It could react with itself and give you some other substance. And here you've got two different collisions. Bi means two, so there you go. Termolecular. You've got three different molecules that have to collide. Now the termolecular, oh wow, this is going to give you just a bunch of stuff. Don't know, there's all kinds of different ways it can sort of rearrange. But these are pretty rare, because if you think about it, when two things collide, if it's going to create a new product, it's got to happen with the right energy. And again, think of the prom date fun. It's got to be the right orientation. And for three things to hit each other with the right energy and the right orientation is pretty rare. So we don't come across the termolecular that often. Mostly we've got unimolecular and bimolecular. Now how does this relate to the stuff that we've already talked about in terms of rates? Well, some of these steps are slow and some of these steps are fast. The rate of the reaction is going to be determined by your slowest step. It's kind of like if you run a relay race, you are only as good as your weakest link type of idea. And we call this the rate determining step. Rate determining, there we go, step. And so this is the thing that we use to write our rate law from. So whatever mechanism, whatever step in the collisions, and say some of them will have multiple steps to it, that's the one that we're going to write our rate law based on. So chemicals that appear on the product side and then eventually disappear, we call reaction intermediates, or just simply intermediates. Intermediates. Yeah, really, I just kind of call them the intermediates. So they are things that kind of appear and then disappear. They're things that are temporarily created but are really unstable, and then because they're so unstable, disappear, and so you don't really see them as part of the overall reaction, but are things that do appear in various places. So for the reaction, and what we do is we kind of propose different mechanisms. How do we think these molecules are colliding? So we come up with different mechanisms, and for us to say, yep, this is a viable mechanism, this is not, it's got to agree with a couple different things. First of all, it's got to agree with the known rate law. So based on experimental data and calculating what the rate law is, I've already seen how to do that, what does it actually agree? And the other piece, it's got to agree with the stoichiometry of the basic reaction. Wow, I'm having spelling problems today. So let's kind of go through a couple examples. Okay, so here's our overall reaction. NO2 plus fluorine gas gives you NO2F. And suggested mechanisms in a series of steps. So this would be a bimolecular reaction where you've got a couple different steps. If this is the correct mechanism, what would be the rate law? Alrighty, so remember that the rate law is based on the slowest step. So here's my slowest step. So this is the reaction that I'm going to write the rate law based on. But let's just kind of dissect the pieces and see what's going on. So kind of like what we did with Hess's law and all kinds of different things, if I add step 1 and step 2 together, these two reactions together should give me my overall reaction. And that's part of the, does it agree with the stoichiometry? So you want to look for things that might cancel out, that you might be able to add together, and the like. So if we look at step 1 and step 2, we see we've got NO2 and NO2. So my stoichiometry is going to give me 2 NO2s. So that's looking pretty good. I have an F2 in step 1. So I like that. But then notice in step 2 I've got this F. F, what is F? Well, it's just fluorine, and it's pretty darn unstable. Notice that there's a fluorine over here on this other side. The fluorine, this is called our intermediate. Notice that it appears as a product, but then disappears as a reactant in the next step. So in the slow step, it produces the F, but F is very unstable. F doesn't like to be by itself, so it's going to quickly get together with the NO2 over here. So notice in the fast step, it's going to quickly bind up with that NO2 to create something else. So my F's are canceling out. Whatever appears as a product and then disappears as a reactant. Yeah, you see it first on the product side and then on the reactant side. That's how you know it's your intermediate. So then I look and see what I've got left over. NO2F, NO2F. It does in fact agree with the stoichiometry. Now let's look at the rate law, see if it agrees with the rate law. Rate laws are based on the slowest step. So this would be K to the NO2 to the first power, F2, no wait. Yeah, I'm good. Never mind. Okay, so we got F2 to the first power. Now, if you're wondering where I get these exponents from, and if you're looking at this overall equation, you're like, wait, that says 2 NO2, and there's only 1 F2. The rate law is based on the slowest step, so you use the coefficients from the slowest step, not the overall reaction. So I really can't agree with any sort of rate law because I just wrote it. So there you go. There's the answer to that problem. All right, another one. The rate law for this reaction is, there it is, which of the following mechanisms is consistent with the rate law? So let's just kind of take a look at both of these things. 3 steps to step 1. I got a fast, I got a slow, I get a fast. Okay, option number 2, slow, fast. And the question says justify your answer. So I definitely need to make sure I got some words that are going to help me justify that information. I'm going to start with option number 2 because it's looking a little simple. So let's take a look and see, does that agree with the rate law? And then also check it with the stoichiometry. So remember that rate laws are going to be based on the slowest step. So if I write a rate law for this particular reaction, it's going to be like this. Well, I already know that the rate law is this, so that's not going to work. The other piece is, does it match up with the stoichiometry? So just remember this sort of distributes over everything. And indeed, that is not going to match up with the stoichiometry very well. Well, actually it does match up with stoichiometry. Why? Because this F goes away. Okay, so it does match up with stoichiometry. However, it does not match up with the rate law. So let's look at the next one. Look at this first step right here. Equilibrium. Notice that little arrow. So that means when this system is in equilibrium, remember you've got concentrations of kind of both things. That's going to be kind of important as we write these rate laws. So first let's just kind of double check the idea of the rate law. If I'm going to write a rate law for this reaction, and you guys are like, okay, it's based on the slowest step, so we're going to go ClO2 F2. Done. Well, let's look at the stoichiometry. Is there ClO2 F2 anywhere in this reaction? No. So we have a little problem. Because it's not in the reaction, what is it called? This is actually the intermediate. notice that it appears, let me do a different color here, it appears here as a product, now here it is a reactant, and then it disappears. So ClO2F, this is actually my intermediate. So since it's an intermediate, it's not part of my overall reaction. And the other thing that I know is since this is an intermediate, and given in the first step, we see that we're at equilibrium. If I know my concentration of ClO2F2, that means I know my concentration of ClO2 and my concentration of F2 because it's at equilibrium. So what I can do then is just sort of substitute that in to my rate law. I use the coefficients excuse me, from the reaction from that particular step, so that's why it's not ClO2 squared or ClO2 to the second. I don't use these exponents, I'm using the exponents from the particular steps. Alright, example number 3. Example number 3 is pretty typical of what AP likes to do on the exams, where you got a bunch of different pieces together. And so we'll see how everything we've learned sort of comes together for a typical AP question. Alrighty, so I've kind of made this up a little bit. So we've got some data for similar reaction. 2A plus B gives you C. Question A, what rate law is consistent with these data? So with these little data points, what is our rate law going to be? So we're going to use our method of initial rates to figure this out. So let's take a look at our data and see if there's anything that we could possibly cancel out. Are there any two experiments that have the same pieces of information? So I notice right here, I got initial concentration of A being held constant. None of my B concentrations are being held constant, so, but that's okay. But I'm going to work with these two first. So remember our method of initial rates. We're going to take two experiments. So I'm going to take experiment 3 and divide it by experiment 2. I like to do the bigger one divided by the smaller one, just because it's going to give me my whole numbers. So I'm going to write the rates. And this is equal to K times 0.5 to the X times 0.05 to the Y divided by K, 0.5 to the X, 0.15 to the Y. Use your fabulous math skills to see what can kind of cancel out. This is going to be a no-brainer. Okay, 6 divided by 2. We can figure that out in our heads, right? That's 3. What else can I cancel out? Well, my K's are going to cancel out. It's 0.5x. 0.5x is going to cancel out. So that leaves me with 0.05. Did I put in the right numbers? Oops. I got to flip these. Like, that's not right. This should be 0.15. Sorry about that. 0.05. 0.15 divided by 0.05. Like, the math should be easier than this. Which gives me 3 to the y power, and y is going to be equal to 1. Now I can solve and figure out what my x is. So pick any two experiments. It doesn't really matter which two you pick. For some reason, when I walked through this, I picked experiment 1 and experiment 2. Because you already know your x value, you can pick any experiment from there. So we got experiment 2 over experiment 1, because experiment 1 is bigger. This equals 0.3 to the 1 to the first power, because I know that. K is in there. Forgot my K. 0.1 to the y. Nope. No. Yeah, the 0.3 is to the x. I knew that. And the 0.1 is to the, I already know my value for y, so I don't need to write y in there. I know my value for y is 1, so I'm just going to plug that in. Divided by k to the 0.5 x, 0.05, 1. Don't go back. Don't want that. Okay. So the 0.05 is to the first power. So let's see, what can we cancel out? So 4 divided by 2 is 2. 0.3 divided by 0.5, this is going to give me 0.6 to the x power. So I'm going to multiply that. Oops, parentheses in the wrong spot. I'm going to multiply that by 0.1 divided by 0.05, because I've already raised those to the first power, so that's 2. And this is going to give me an x of a 0 power. So now in terms of the rate law, and I realize I just didn't give myself a whole lot of space, I'm just going to write the rate law up here. My rate law is equal to k to the, what are my concentrations? I got a to the 0 power, and b to the first order. Okay? Since this is to the 0 power, really the rate law should be k times b to the first. This would be your final answer for your rate law. Alright, next step. Calculate k, and remember that the rate constant has units that go along with it. So let's write our rate law and solve for k. So in figuring out what the value is for k and so forth, just pick an equation and start plugging in numbers. So I'm just going to pick the first one. 4 times 10 to the negative second equals k times 0.3 to the first. And then k gives me an answer of 0.4 units. Do not forget your units. When all you do to figure out units, dimensional analysis. So it's seconds to the negative 1. Moving right along. Let us see, how long will it take for the concentration of C to equal the 0.1 molar, to equal 0.1 molar, if your initial concentrations are blah blah blah. Alrighty, how long? This implication of time means that we're going to need to use the integrated rate law, because that is the equation that relates time with concentration. The differentiated rate law relates rates and concentration. So this is, we're kind of looking at seconds and so forth. So we've already established what order this reaction is. Since it's b to the first, it is a first order reaction, which means I'm going to use the first order integrated rate law, which is this. Now, yes, these equations are given to you on the free response. However, there oftentimes are multiple choice questions that expect you to kind of be able to use these, you know, using some friendly numbers, they say. So do plug these equations into your head. It would be helpful. So here you go. There's your first order integrated rate law. Now, I need some concentrations, because my natural log of b, that means whatever my concentration is at that particular time, which given I have initial concentrations, but I don't have when I'm done. And then b sub 0, this is going to be my initial concentration of stuff. So how do I figure out the numbers to plot into this thing? Well, remember once upon a time, we used these things called tables, right? And so our overall equation, if it's 2a plus b gives me c, I'm just going to rewrite that since we're looking at it. I can use our fabulous little Picard table to figure out what the concentrations are at any given moment. So what do I know? I know my initial concentration is 0.4. I know my initial concentration of B is 0.3. Starting off with 0 of this. I want to know how long it takes to get to this amount. So when I'm done, this has to be at 0.1, which means this side's going to go up by 0.1. This side is going to go down by 0.1. So my change is going to be 0.2 when it's all done. Now notice the stoichiometry. I got a 2-to-1 ratio here. So this isn't going to go down by 0.1. It's going to go down by 0.2, which means my final concentration is going to be 0.2. Now when I plug these two numbers in, where was I? Oh, plugging in concentrations there. When I'm plugging in stuff to the rate law, notice that though A is not part of the rate law, so I really don't care about that piece. But now my key pieces of information here, I've got B and I've got C, so now I can plug in, well, I don't need C either, but I got B. So I need to plug those numbers into my integrated rate law. So now I'm all good to go. I'm going to do, let's see, natural log of 0.2 equals negative 0.4, because I've already solved for k, because remember this is negative k. In letter B I got my value for k, times t, that's my ultimate goal, times the natural log of my starting concentration, which is 0.3. And when you go ahead and solve for t, you end up with 7 seconds. So it would take 7 seconds for this reaction to hit 0.1 molarity given these particular concentrations. And to me, that's kind of the coolest part about kinetics and this whole unit is like, how long will it take for this reaction to give me what I want? And that's really what industry cares about. Letter D, the mechanisms. Which one is the most consistent with the observed kinetics? So now you know your rate law, and so we got to go back and not the integrated rate law, but the differentiated rate law, the rate law. Remember, it's based on the slowest step. So let's just kind of look at our 3 options and write our rate laws and see what agrees with what we've already accomplished. So there's the rate law for the first one. Here's our rate law for the second one. Here's our rate law for the third one. And just right off the bat, hopefully you can kind of see which one wins, and that would be this one. Yay! All right. The last little piece of this unit, catalysis, which has nothing to do with cats, but it has everything to do with the idea of a matchmaker making this reaction. So everything we've kind of done with these different mechanisms is, again, totally based on the idea of the collision model. And you got to think about what factors make a successful reaction. The right orientation. Are the molecules hitting each other in the right way? Are you hitting the girls in the books, or are you hitting them in the wrong way? We must hit them in the books. Yes? Okay. So orientation is a big deal. The right amount of energy. Not too much, not too little, but how well are you hitting the girls? How well are these molecules being hit? And where this kind of comes in with these graphs is this idea. I'm going to look at this little graph right here. You know, actually, I'm just going to draw one. These get a little fuzzy. Okay, so say this is a energy diagram or a reaction coordinate diagram. There's lots of different ways you can say it. Here's your reactants, the energy that the reactants are bringing, and the energy that the products then contain, the potential energy of it. So when we say, what if are you hitting it with enough energy, that is actually kind of referring to this thing known as the activation energy. And it's kind of symbolized AE. So in your reading, you should have come across this thing called activation energy. Actually, your book uses EA. Sorry. Your EA is your activation energy. It is the minimum amount of energy. I should just write first. There we go. Activation energy. There we go. The minimum amount of energy required to initiate a chemical reaction. So that energy of hitting the girl just enough to make contact, but not piss her off, right? And to create kind of what we call the activated complex. And when we talk about like the mechanisms, what sort of intermediates does it make? That is what where we're getting at, this little activated complex. What is this middle step as things sort of glom together and get ready to become the products? Now, the other cool things about these diagrams, hopefully you've kind of figured out, if you go the distance between the reactants and the products, this is your heat of the reaction, this is your delta H. And you can tell just by looking at this graph that it is exothermic. This particular graph is an exothermic reaction. Heat is being released. So you can imagine what an endothermic graph would look like. It would kind of be the opposite. That's a really weird curve, but you get the point. Okay, my point is, back to catalysis. When we had the matchmaker, what the matchmaker did was make it easy for you to have the collision with the girl without as much violence. So what the catalyst does is the catalyst actually lowers this activation energy. So the graph is going to be less of a hump there. So it's a substance that speeds up the reaction without being part of the reaction, just like part of the overall reaction. Just like the matchmaker does not become part of the prom date couple. And it does this by lowering the activation energy. How it does this is it changes the reaction mechanism. So that series of steps, it'll actually kind of change how the molecules sort of collide. Down here, these are our Maxwell-Boltzmann energy distributions, and so it's just kind of showing how many molecules have enough energy to collide. And so this would be, you know, something that doesn't have a catalyst involved, and then this one that does. Notice that with a catalyzed, it's a hard word for me to say, reaction, a lot more molecules have enough energy to create, to make the reaction happen. Incidentally, there is an equation that shows up on your handouts that AP gives you to calculate the activation energy, and it looks a little something like this. It's K to the A, E, the activation energy, minus, and this is like an exponent thing, negative EA RT. So we'll be using that in a lab a couple times just to kind of get the hang of that piece. So I said it changes the reaction mechanism. So how do you recognize it if you're looking at a series of steps? So here's our, okay, so let's look at these two particular steps, following a mechanism. Determine our overall reaction. To figure out our overall reaction, we want to see what cancels out and what are we left with. So let's see, I have an O3 here, I have an NO there, and I have an NO there. So that NO, that's going to cancel out there. I have an NO2 here, and I have an NO2 there, so that's going to cancel out. I got this O and an O3 and a couple of O2s. So my overall reaction for this is going to be O plus O3 gives me 2 O2s. So what are these NOs and the NO2s and all that sort of stuff? What you have to do to pay attention to, or to figure out what is a catalyst and what is an intermediate. What is an intermediate? It's something that is created as part of the step and then disappears. So the NO2 is the intermediate because it's created as a product and then goes away. The NO is a catalyst. It's there in the beginning, it's there in the end, but is not part of the overall reaction. Incidentally, NO, nitrogen monoxide, is one of those lovely little greenhouse gases. It's created by your cars. And so how is that responsible for like destruction of the ozone layer? Well, it's getting up there into the ozone layer and catalyzing this reaction, speeding it up, breaking down the O3 into the oxygen gas. And I remember reading somewhere it's like 1 molecule of NO has the ability to catalyze like 30 million ozone molecules. So yeah, that's part of how the ozone is getting depleted, is because of these catalysts that we're releasing into the air. All right, let's take a look at another, on that cheery note, another example here. The reaction proceeds, blah, blah, blah. Okay, determine the overall reaction, which substance is the catalyst, which substance is the intermediate. So let's kind of go through the same idea with our little steps here. What is our overall reaction going to be? Oh, precedes, I can read. My CLs kind of cancel out there. My CLOs are kind of canceling out there. So, well, isn't that interesting? We have the same reaction, the same overall reaction, breaking down in the ozone layer. What is our catalyst? So our catalyst is a thing that's there at the beginning and then goes away, and that would, or it's there in the beginning and it's there at the end. So our catalyst is the chlorine. Okay, not ClO2, just Cl. What is our intermediate? That would be the thing that's created but then disappears. So that's the ClO. All right, last idea is that there are two types of catalysts, homogeneous catalysts and heterogeneous catalysts. Homogeneous just means that it is the same state as the reactants. And by state, we mean phase, solid, liquid, gas, what is it? A heterogeneous state, these are going to be different. Different states. So for instance, cars have a catalytic converter. They use a catalyst. It's usually like a piece of platinum, a solid piece of platinum, that it takes the nitrogen monoxide, byproduct of the combustion engine, and really just kind of breaks it down. So it's sort of like, you know, here's the nitrogen monoxide gas, and then, oh, let's make the platinum green. The gas sort of goes over this solid piece of platinum inside your catalytic converter. So you've got a gas passing over a solid, and when it does that, it harmlessly breaks these things down into gases that are not quite as toxic. So that's why we have catalytic converters on your cars. There's all kinds of biochemical catalysts as well, like enzymes. Pretty much every single biochemical reaction you can think of is really, really slow. So there's lots of enzymes that kind of help speed it up. Things like lactase, all those hydrogen peroxidase, all kinds of, you know, all the enzymes end in A's, and their sole purpose is to speed up the breakdown of some sort of, or speed up a chemical reaction, so breaking down of sugars and whatnot. And that, ladies and gentlemen, is the end of Chapter 14, Chemical Kinetics. Hope you guys are having a great day, and I will see you later.